Okay.
Good afternoon, everybody, and welcome to today's MIRACUM DIFUTURE Kolloquium. I also welcome our today's speaker. It's Suteera Seeha from the Technical University in Munich, and she has given her presentation already in this year May at MIR in Glasgow. However, not everybody of us had the chance to follow her to Glasgow, so we are eager to hear about her research results as well in our colloquium presentation. And I'm sure she will explain the 3 abbreviations in her title as well in her presentation. So please start, Ms. Seeha.
Thank you. My name is Suteera Seeha. I am from the chair of medical informatics from the TUM University, and in Munich. So I'm very happy to be here, and I'll be presenting the work from my group. The title of my talk or our paper is German Medical Name Entity Recognition, or NER, with BERT in large language models, the impact of training data sets. Okay, so a little bit about me. I am a PhD student, and I am the member of the junior research group called DEXT, where we work on clinical NLP. And I have a background in computational linguistics. My research interest is in information extraction, knowledge graphs, and question answerings. So let's start. Imagine you are a doctor and you work in a hospital. Every day you generate lots of unstructured data. These can be discharge summaries, physician notes, pathology reports, or radiology reports. And these documents usually contain useful information that you might want to use it. For example, pathology report or past treatment recommendation. You might want to take a look at the historical data to make suggestion for a current patient, for example. So there are lots of insights in this data. However, much of this data is underutilized because they are not in the form that is ready for analysis. So there are many things that you can do with unstructured data. For example, as a data integration center, you might want to integrate or extract information out of this data and integrate it into your data integration center. Or as a doctor, you might want to integrate relevant information to the EHR system, or use it in the clinical decision support systems, or just apply medical coding on it. So to make this possible, the first step that you have to do is to extract meaningful terms or entities, something like itchy skin, runny nose, watery eyes, which are symptoms, and something like medication or diagnosis, depending on your use case. So the process of extracting the span and applying the predefined class to the span is called named entity recognition in natural language processing term. In this work, we will refer to it as clinical name entity recognition because we work on clinical text. And for many downstream applications, name entity recognition component, it's very important. So usually we want it to have high accuracy because it can affect the performance of the entire system quite a lot. And although there are many commercial tools for medical NER, we as a hospital or the DITs, we might not be able to use them because we work with real patient data that is sensitive data. So large companies like Amazon, Google, Microsoft, they have tools for analyzing medical data but these are for English, mainly for English. We also have other open source tools. There's lots of large research on this topic, but most of the tools are focused on English text, and they are trained on English text, so it's not ideal for German hospital. And also, these tools might not be ideal to use for our particular data, which had like a slightly different data distribution or a particular domain of your interest. So now if we consider training our building our NER system, we have some consideration to make. The first one is that the annotated data for German language is scarce, and to build an NER system, for example, based on a large language model, we need annotated data. And also another consideration is that most hospitals, we don't have good infrastructure in terms of a large GPU for training a big large language models. So our work is motivated by these limitations. So we are particularly interested in using large language models for NER because it has shown to be really powerful in many fields, including medical NER domain, and because there are many open source language model that we can use from small size to medium size to the big one, which is a good choice to process hospital data. So, however, it comes with like various size, various trade-offs. This model. Now, the question now is that we as a hospital with this limitation, which one should we choose? Should we choose something small or something big? Like we kind of know that bigger model performs better, but is it really the case? And the fact that we have to work under constraints like the GPU, we don't have like a very big GPU, or we might not have a large amount of training data, considering like some domain that do not even have publicly available annotated data. So if we want to do NER on it, we might have to annotate the data on its own, on our own. Yeah. So to explore this, we create our research question as follows. Do we really need a large model to perform clinical NER in German? Or can a small model like the BERT model can do the job just as well? And to explore this, we compare fine-tuning the LLaMA model and the BERT model on the NER dataset and see how they perform in low resource setting. Low resource means that we have a small amount of training data. This is again like the detail of our method. We pick one small model. Here we choose the GBERT model, which is a mass language model with 110 million parameters. And it is trained on German text in general domain. And a representative for a large model, we choose LLaMA3.1. At that time, it was the best one with 8 billion parameters. And LLaMA is trained on general domain as well, but it's also trained on German text. So we fine-tune both models on 2 German NER datasets, and we see how do they perform with limited training data. We use the entity level F1 exact match as an evaluation matrix. The data set, we use the GBERT 2.0, which is a corpus of oncology guidelines. In German text, it has, in German language, sorry, it has 7 entity types, for example, diagnosis or pathology, clinical drugs, and diagnosis. And I can show you an example of the data set as well. So this is how GBERT looks like. So this is the text and the annotation. Another data set is the cardio DA. This is a corpus of doctors' letter from cardiovascular domain, also from German language. It has 6 entity types: drug, duration, form, frequency, and so on. Again, this is the example. Next, I will talk about how we fine-tune the model. So to simulate the low resource scenarios, we create multiple training subsets. So we have the training set, and from the training set, we create a subset that is 20% of the original training set, 40%, 60%, 80%, and 100%. And for each subset, we also make sure that it has a balanced distribution of entity types so that all categories are fairly represented. And then we fine-tune our model on each subset and then train it on the same test set. We do the same for like LLaMA. Okay, before we go to the results, I would like to explain about our evaluation matrix. So entity level exact match. So exact match means that the model has to predict exactly correct as a ground truth. For example, given this text, the goal span is insulin aspart with the type activing, and the model has to predict exactly like this in order to be seen as correct. So this is entity level. And a not exact match or a partial match would be that if the model predicts only insulin, we might consider it as correct as well. So this is partial matching or relaxed match. But in our work, we use exact match, which is a more restrict score, let's say. And another point that I want to explain is entity level. So in name entity recognition, there are two types of evaluation, which is token levels or entity level. Token level, for example, here you would see it as two tokens, insulin and aspart. But as an entity, it's only one entity. For example, if the model predicts insulin aspart, which is exactly correct, the same as the gold standard, we consider for the entity level, we consider it as correct and one correct item. For token level, is two items correct, which is insulin and aspart. And when the model predicts only insulin, for the entity level, it is wrong, although it kind of predicts partially correct. For entity level, it's one correct and one wrong. So this is the difference. So let's look at the results. The first observation, okay, maybe I explain the graph first. So this graph, it's the result of the GGPyong dataset. This one is for the cardio DE dataset, and the x-axis is the F1 macro average, and the y-axis is the percentage of the datasets from 0 to 100%. But we are going to look at 20 to 100%. The blue line is LLaMA. The pink line is BERT. The first observation is that we see that the more data we give to the model, the better they perform, which is something that is expected. And the best performance on GGPyong is 64% F1 score from LLaMA, while BERT made 60%. And on cardio DA, BERT actually outperformed LLaMA at 80%. So it has 81 F1 score, while LLaMA performed slightly worse. Yeah. Okay. The next observation, we found that overall on GGPyong, if we look at GGPyong, both of them perform quite similar. You can look here, the dots are very close, while BERT has like a drop at 60% of training data. However, LLaMA performs slightly better overall on this data set. Now, if you look at cardio DA, this data set seems to be difficult for BERT. Here we see the blue line is always like above the pink line, even though eventually BERT did outperform LLaMA. We can see here that the performance gap is larger. So LLaMA performed quite a lot better, especially when the training data is smaller. when the training data is large, like 80%, 1 to 100%, both models perform similarly. And okay, now if we look at a pattern, we will see that BERT has like a sudden drop and here a sudden peak. This could indicate that like overfitting, that BERT is maybe more sensitive to outliers than LLaMA. If we look at the blue line compared to LLaMA, the blue line is more gradual. It has a drop here as well, but it's more gradual. Yeah. So we also did error analysis. We found that LLaMA suffers from hallucination. So LLaMA hallucinate both entity span and entity types. In terms of entity span, it's 2% out of the span errors, but the error is not very crucial because it's mostly try to apply grammar correction, such as like adding s or something like that. And it also hallucinates entity types with 0.2% out of all type error. However, we found that the hallucination occur less and less with more training data. On the other hand, BERT does not show any hallucination because it's not a generative model. It's just because of the model, the design of the model. It's not possible to generate hallucination. We also look at two more types of errors. The first one is complete wrong span, and the other one is partially wrong span. So completely wrong span means that, let's say the green part is the ground truth, is the expected answer, but if the model predicts something like preparata, it's completely wrong. And partially wrong would be that the model predict maybe only insulin. Yeah. This is the goal of this is to see how the model behaves. So out of all error of BERT, it's mostly predict completely wrong spans with 62%, and with LLaMA, LLaMA predicts so make both sides of error in the same amount. If we look at the computational resources, the small model require less computational resources as we expect. So BERT only requires 60 gigabytes of GPU utilization during training, while LLaMA requires 48 gigabyte GPU. And to train one epoch of BERT, it takes only 30 minutes. And with LLaMA, it takes 2 hours. So the training of LLaMA is 4 times slower than BERT. So we arrive at a conclusion. As a recap, what we did in this work is that we compare a small mass language model, which is GBERT, and a large generative model, LLaMA3.1, in name entity recognition tasks for German clinical domain. And we focus on observing how the model performs when the training data is limited. Our results show that both models can reach very similar performance. With LLaMA or the large model performs overall slightly better, especially when the training data is limited. The large model LLaMA performs better than BERT. And we also found that BERT seem to be sensitive to outliers and might overfit easily. However, LLaMA has that disadvantage that it hallucinates and require more computational resources and time. So some takeaway, we can go back to our research question, do we really need a large model? So my answer would be depends on your situation. So if you have small data set, it may make sense to use a large generative model. But if you have a large data set or high quality one, it might also be a good idea to use a small model to save time, and also it can achieve a similar performance at the large model. But here you have to make sure that your small model is not sensitive to outlier. Let's say like if you pick GBERT as we did, we might have to make sure that the annotation is high quality because the models seem to be very sensitive to outliers. That's all. Thank you. If you want to reach me out for collaboration or something, write me an email. Thank you very much.
Oh, thank you very much for the very nice presentation of exciting research. Is there any question to Suteera, Seeha? Matthias Ebel is raising his hand.
Yeah. Thank you very much for the nice talk. I was wondering, for the graph that you showed, did you repeat the model, the experiments a couple of times to see how stable it is? Like especially for the 81 versus 80%.
Yeah.
Might be just by chance.
Yeah. Actually, we did not. We know that we should do that at least maybe 3 times or 5 times, but we kind of run out of time, so we didn't do that. But I agree that it would be a more reliable result if we repeat it a few times.
Yeah, would also be interesting, especially for the lower training data percentage, like how far the performance actually is. But yeah, thanks.
Yeah, it's a good practice to run multiple times, but yeah, we didn't do that.
There was a second hand up before, but now Stefan Lenz.
Hi, yes, I just want to ask. So in these curves you see here, there are no. This is only the performance on the training data, or did you also have some separate test data? Because there is, I don't know, maybe the issue of overfitting, that a model becomes very close on the training data, but maybe on other data it might not be that extrapolate that well. So I think in general, like big models have maybe if they are trained very much, they have the tendency of overfitting. If they're not trained so much, they also might generalize better than the smaller ones.
Maybe the graphic is not good. Actually, this is the result from the test set. So this is although we write percentage of training data, this is the result on the same test set for all of the cases. Yeah. So as we show here, maybe this graph is maybe not the best one, but yeah, we fine tune on this training set, and what we reported is F1 from the test set.
Would you just come back the slide you showed before so it's this one, yes. I was wondering, when you have a training set with 100%, what is left over for the test set? Or do you still use complete data as a test set?
We actually have the train and test sets separated from the beginning. And to create a subset, we only use the train set. And we keep the test set separately.
Completely independent then after that.
Okay. Yeah.
Phil, I have a question.
Yeah, I have actually 2 questions. One is along the same line regarding the reproducibility. So we work more with vision transformer models because we're interested in histology, and what we use is this Monte Carlo cross-validation, so that you split your set in a training and a test set, and you do this several times, but with different data sets, from the same overall data set. Is this something that you can do also with these small or the large language models?
I think so. You talk about cross-validation, right? Yeah. So in NLP, we also do that. But unfortunately, in this work, we didn't do that.
Okay.
It would be
because
possible,
that would be the multiple runs, right? To check whether it's really reproducible.
Again, I didn't understand that part.
I mean, that would be one way of doing multiple runs, so that you don't do the the multiple runs with the same split of
I see.
training and tests data sets, but that you split your overall set just differently each time, but to see whether this is reproducible.
Yeah, that would be a good idea. Yeah.
And then another question would be like a little bit the outlook. So obviously, if you look at natural language processing, it would be one first step, the name entity recognition. But it wouldn't help you if, for example, it's written in a report, this patient has a glioblastoma, or it's written the patient does not have a glioblastoma, right? This would not be detected. So the next step would be the context and the relation. Is this something you're also working on, or what are your ideas on this?
So also regarding name entity recognition, the task is actually to extract those like clinical terms. So we actually do not consider like negative. I'm not sure, like most of the system do not really consider like negation, for example, not or no, things like that. So this is the general task, but it has to do with your I think either we want to consider context or not. It has to do with the thing that you want to do as well, the application. Like I would say considering like negation and other things in this task, it may not be really relevant. But for something like we want to draw some conclusion, summarization, or do question answering, definitely you have to use the model that can understand the whole context. And although our model, like the BERT and LLM, they do take consideration of the context, so we feed the whole text to the model. But I would say it wouldn't affect the result much. Either we consider like the negation or not, or like I'm only talking about negation, but of course, like you have to understand the whole context in order to know whether this particular span is medical term or not.
There is no more additional external questions, so I have a final question. You have mentioned in your conclusion that larger data sets are better for training. The question is, you have produced smaller and larger data set in a simulation way by splitting a given data set. The question I would have would be, at which size is the data set, small or large? Could you, sorry, could you explain this a little bit?
So, I mean, there are different ways to answer this. I mean, it could, like I read at some point that a good amount of training samples for a machine learning model is 8,000 points, like data points. This is the minimum amount. So that's something that I read. But I would say, if it's going to be like my own answer, yeah, it's quite relative what is small and what is large. And
so as a hint for external researchers who do not want to do this as a simulation, I would think it would be helpful to continue the research in order to really find some thresholds where the quality of a small model would decrease, starting up from which size of training set.
I think to do that we might need like a larger training set. We only have like these two German data sets, which is also actually quite small. I don't have the number here, but they're not very large. And the research that did like similar thing, like similar experiments, we do it in this kind of way because just the trend that we see is also cut off tail something. But yeah, you're right that maybe if we increase more data, we might see some more information. how the model behaves. Yeah, but I would say from our results, we kind of already see that it kind of improved so much at 80%, and here it's even dropped. Yeah, we're also not sure why. Yeah.
Okay.
It could be many variables. Could be like also the LLMs start like overfitting. What we did not really study that. Yeah. Thank you for the question. Very interesting.
So there's no more questions. So thank you again for the very interesting presentation and the discussion. And I hope to see you all again in our seminar in next week, Tuesday next week. Have a nice evening and a nice week. Goodbye.
Thank
you very much for
Bye-bye.
the presentation.
Bye.